When you arrive on the scene of a hazardous materials emergency, you have several concerns on your mind. You must obtain information on the hazard and the conditions to determine the level of response required. You must decide whether responders can be adequately protected and decontaminated. And you must be prepared to adapt when conditions change to ensure the continued safety of team members and the public. One of your most valuable resources for recognizing hazards and keeping on top of potentially dangerous conditions is your detection equipment. If you're thoroughly trained in the operation of each device and the interpretation of its data, detection equipment can help you make life-saving decisions. Hazmat detection equipment ranges from very simple paper test strips to highly sophisticated digital readout devices. Few departments are equipped with every detection instrument on the market. Decisions regarding the instruments that your department needs should be based on the hazards you're likely to encounter. Pre-planning will provide valuable information and help you make the right choices. Your hazardous material unit may carry as part of your equipment inventory one or more of the following: a combustible gas indicator, usually referred to as a CGI, an oxygen meter, a photoionization detector, an organic vapor analyzer, specific gas meters, such as those used to measure carbon monoxide and hydrogen sulfide, detector tubes, which are also used to monitor specific vapors or gases, radiation detection devices, and test kits for identifying liquid and solid hazards. The combustible gas indicator, or CGI, is one type of detection equipment with which you're probably already familiar. A CGI is used to measure the concentration of a flammable vapor or gas. The reading on the instrument, however, is a percentage of the lower explosive limit of the gas. It does not represent the percentage of the gas in the air. The CGI is usually calibrated to methane and will respond accurately only to that gas. How the CGI will respond to other gases and vapors can be determined from manufacturer's information. This relative response of the instrument to other vapors and gases may be more or less sensitive than its response to methane. You'll recall from the first module that the lower explosive limit is the lowest concentration of a vapor or gas that will support combustion when exposed to an ignition source. A reading of 100% of the LEL on the CGI means that the atmosphere is readily combustible. When the gas or vapor concentration is above the upper flammable limit, the atmosphere is too rich to burn because the gas has displaced the oxygen that's necessary to support combustion. In this case, the meter needle will rise above the 100% mark and may then return to zero. Check the manufacturer's instructions to see how your specific instrument will respond in these cases. Keep in mind that ventilation of this area, a necessary fire department objective, will result in the concentration of the gas falling within the flammable range. A CGI typically works by burning a sample of gas. This raises the temperature of an internal filament, which results in a readout. Oxygen must be present for the gas to burn. Therefore, the CGI can't produce an accurate reading in an oxygen-deficient atmosphere. Also, the presence of lead and certain silicon or sulfur compounds can destroy the device's sensing component. Finally, a CGI is limited in that a concentration of a gas could register well below the lower explosive limit and still be extremely toxic. A relatively low concentration of toluene, for example, may not be flammable. But this same concentration may result in severe effects on the central nervous system, such as weakness and confusion. The CGI you use must be certified as intrinsically safe or explosion-proof for use in the atmospheres you'll be sampling. All certified devices are marked to show the class, division, and group of hazards that they can safely monitor. An oxygen meter is used to detect the level of oxygen in the atmosphere, typically in a confined space. An oxygen meter may be used in conjunction with a combustible gas indicator to verify that there's sufficient oxygen for the CGI to operate properly. Oxygen-deficient atmospheres have resulted in the deaths of several emergency response personnel. Oxygen-rich atmospheres are also dangerous. As you'll recall from the chemistry module, such atmospheres support very rapid combustion. Environmental conditions, such as temperature, altitude, and barometric pressure, can affect the readings of an oxygen meter. In addition, some gases, such as carbon dioxide, can interfere with the instrument's response. Remember that an oxygen meter can't detect the presence of anything other than oxygen, but a low reading may indicate that oxygen is being displaced by some other material in the atmosphere. This may happen on terrain where gases have pooled, as was demonstrated in an earlier experiment. A photoionization detector is a general survey instrument that can detect low concentrations of some organic and inorganic vapors and gases. Photoionizers don't identify toxic chemicals. They only tell you the relative concentration of vapors and gases in the atmosphere. A photoionizer uses an ultraviolet light source to ionize gas or vapor molecules. The ionized electrons are collected on a charged plate, and the total number reflects the concentration of the gas in the air. Although it's very useful for general atmospheric monitoring, the photoionizer does have limitations. For example, it's more sensitive to complex compounds and less sensitive to simpler ones. As a result, it may not be able to detect dangerous concentrations of simple compounds, such as carbon dioxide and methane. To use a photoionizer correctly, you must have a thorough understanding of all the components of the instrument, as well as an accurate identification of the hazard you're monitoring. As its name suggests, an organic vapor analyzer detects the presence of organic vapors in the air. Unlike a photoionization meter, an organic vapor analyzer, when properly equipped, can be used qualitatively as well as quantitatively. That is, it can help you identify a chemical as well as its concentration. Organic vapor analyzers can only detect gases or vapors that contain carbon. For example, this instrument is frequently used to check for leaks in natural gas lines. Like photoionizers, organic vapor analyzers ionize molecules and collect electrons to measure the concentration of a substance. However, the organic vapor analyzer uses a hydrogen flame rather than an ultraviolet light in the ionization process. There are certain instruments, like this carbon monoxide meter, that are designed to provide accurate responses to specific gases. These instruments usually measure the concentration of one specific type of gas only. However, some of these meters have more than one detection device and can be used to monitor more than one gas. These types of meters register a response when the sampled gas is drawn through a detector and generates an internal chemical reaction. Like oxygen meters, specific gas meters can be adversely affected by environmental conditions and by certain gases. Detector tubes, sometimes known as colorimetric tubes, also quantify gases. These tubes are designed to measure the concentration of a single gas or vapor in the atmosphere. Because each tube is manufactured to react with a specific gas or a small group of gases, it is most effective if you know the chemical you're monitoring. Detector tubes do not require calibration checks as most other instruments do, but they do have expiration dates that must be checked before use. These devices are used by drawing in a specified quantity of contaminant air. This gas or vapor sample reacts with the chemical in the tube and produces a change in color. The length of the color change is proportional to the concentration of the contaminant in air. Although they're quite useful for quick sampling, detector tubes have obvious limitations. They may react with gases or vapors other than those for which they were calibrated. Also, the chemical reaction in the tube may not be precise. The reading may differ from the actual level by more than 25%. And, as with other equipment, temperature and humidity affect the performance of detector tubes. There are several different types of radiation detection devices. Survey instruments measure the type and level of radiation surrounding a source. Many radiation meters have interchangeable detectors that are specific to short alpha emissions, the more penetrating beta radiation, or the very harmful gamma rays. Radiation detection devices typically work by measuring the amount of ionization caused by the radiation source. When performing such measurements, remember that protecting yourself by using appropriate shielding and limiting your time near the source is a priority. Personal dosimeters are used to estimate the total dose absorbed by an exposed individual. The detection equipment we've discussed so far is used to monitor hazardous materials in the air, which are likely to be your most immediate concern. However, solids and liquids can also pose problems that can't be detected by air monitoring equipment. Identifying and measuring hazardous solids and liquids usually involves the use of field test kits. These kits sometimes use chemicals to obtain reactions, or more frequently, test paper. Some detection equipment, like paper test strips, is very simple to use, but most of the instruments we've discussed require extensive training and experience. Proper protective clothing is also required when evaluating contaminated or unknown atmospheres. To obtain valid results from detection equipment, you must know how to calibrate or check the calibration, activate and operate the device correctly, and interpret the results accurately. Remember, detection instruments were developed as safeguards. Used incorrectly, they may give you a false sense of security and lead to unwise or inappropriate decisions. Those are the decisions that could endanger, rather than protect, your health and safety.